All right. Hi. Thank you for being here, and I'd like to thank the organizers for bringing all of us to sunny California on this beautiful day. I am really excited to talk to you about metal pollution around massive white dwarfs as a tool to constrain planetary occurrence. And my name is Baya. If you haven't met me, I work at Boston University with J.J. Hermes. This work has been possible thanks to the early efforts of the HST Snapshot team, Boris Gansik, Detlef Koster, and Jay Fari. So we are living through quite a revolution in terms of exoplanet detection. And that's mostly thanks to transit surveys like TESS and Kepler, so much so that we reached 5,000 confirmed planets earlier this year. But there's a bit of a caveat here. That is that when you actually look at the host mass of those confirmed planets, you see that we don't have a lot of constraint on planets around stars of 3.5 solar masses and up. And that's where white dwarfs come into play. So I'm going to give you the punchline right away, and then we're going to go through and sort of figure out the steps of this. But the idea is that roughly 50% of white dwarfs are metal polluted. But then when you look at specific mass bins for this, you see that it happens to be less than 10% of the more massive ones that are metal polluted. And when I refer to massive in this talk, I'm going to be talking about 0.8 solar masses and up, or 3.5 solar masses on the main sequence. So this sort of raises a question of wondering if metal pollution in massive white dwarfs is representative of single star evolution alone, or if other factors could be at play. All right, so let's do a very quick reminder of what happens to planets around stars during stellar evolution. This is a beautiful illustration from Mark Garlick. And you see that at the red giant phase, as the radius of the star increases, planets are disrupted and their orbits expand. So that when we get to actual white dwarf stage, the orbits are destabilized and only planets at very distant orbits may survive. So we've heard a lot about metal pollution today, and C and Mark gave excellent introduction, so I'm not going to go into too much details here. But we've understood that we talk about metal pollution as the accretion of scattered tidally disrupted materials onto the white dwarf. And when we look at the white dwarf abundances, we learn a lot about the materials that could be around that star. And C. Shu had done some great work figuring out that those elements might be like bulk Earth with magnesiums and silicon and iron, things like that. So in order to detect metal pollution, we can look at the photospheric trace metals, and in particular, we look at silicon lines. This is a complete cost spectra from the Hubble Space Telescope, UV spectra, and I'm also showing you sort of a zoom in on silicon lines that are decently strong here. So the sort of takeaway is that metal pollution is usually synonymous of one major surviving planet and a reservoir, modest reservoir of planetesimals. So in 2014, Boris Gansik with Detlef Koster and Jay Fari worked on getting UV spectra of some bright, hot white dwarfs in this snapshot program. And the idea was to find white dwarfs that would be sensitive to metal pollution in a perfect world where they're hot enough so that convection doesn't come into play, but not too hot so that radiative levitation doesn't play too much of an effect either. So they observed about 100 stars, and these are their distribution on some atmospheric parameters like effective temperature, surface gravity. They also have the magnitude here. And their derived masses, mass of the white dwarf, mass on the main sequence, and cooling age. Here, these histograms in black is where silicon was detected, and they assume active accretion. And the gray ones are where radiative levitation could be at play. So we assume likely recent accretion, silicon was also detected. And what you're seeing here, as I spoiled a little earlier on, is that when you look at specific mass bins and the distribution over mass ranges, you might see something a little interesting. That is that the less massive ones, when you look at under 3.5 solar masses on the main sequence, have between 30 and 50% metal pollution. We've heard this number a lot already today. 30 is when you only look at the black histogram here. 50 is when you also take into account the gray one. So this is the rough metal pollution for the least massive ones. But then when you look at the more massive ones, above 3.5 solar masses, that tells a different story, and it drops to less than 10%. Now, I didn't want to keep any secrets. These are extremely low number statistics, and that's why I put the numbers here. At 3.5 solar masses and up, it's only 1 out of 12. So Boris kept getting more data, and in cycle 25 of the Hubble Space Telescope, was able to get a lot more white dwarfs in the same sort of criteria, with even more of a focus on massive ones. And I've been very lucky to work with this sample for the past few months. These are the distributions of the atmospheric parameters and the derived mass that I get from spectroscopy. This is how they lay on the color magnitude diagram. I've highlighted a few cooling tracks so that you have a better sense of where they lay. In the back in gray, that's the Gaia DR3 sample, and the SNAP sample is in blue with the metal polluted objects in red. So this is about 300 stars, and I'm highlighting the same sort of mass ranges here because though we've really increased the sample, you might notice that the distributions look very similar. But we need to look at the progenitor mass to sort of make sure of that. And so what I did to look at the progenitor mass is pretty standard method of deriving white dwarf mass from atmospheric models. I use the Montreal model and Laplace model. And then I use the initial final mass relation to get the main sequence mass. The one I used has been worked by Tyler Hines recently, looking at wide binaries to refine ages. So with that, I'm getting the actual distribution of initial masses. And what you're actually seeing is 37%, plus or minus 6, of metal pollution over the full SNAP sample of over 300 stars. This dissection is with a limit of a logarithm of silicon over hydrogen of minus 7.5. And if that doesn't mean much to you, if we assume bulk Earth abundances, that would be about 10 to the 5th grams per second. If you're better with images, that's like 1 baby elephant falling per second on the white dwarf. So yeah, those are the limits. But I'm showing you the fraction of showing metal pollution as a function of the mass. And this is pretty drastic. I mean, you can see what's happening. We're seeing the same sort of statistical distribution where if you look at the sort of lower mass bins under 3.5 solar masses, it's 46% metal polluted. But then when you look at the more massive ones, it also drops to 9%. I went even further. And if you look at 4.5 solar masses and up, there was actually no detection, which within 1 sigma of confidence gives us less than 10% of metal pollution. So while these are still small number statistics, it raises an even bigger question, which is that we increase the number of stars by at least 3, even probably more for the more massive ones, and we observe very similar statistics. So this makes us wonder about planetary occurrence around those sort of intermediate mass stars. And there is a consensus that a substantial number of massive white dwarfs come from mergers, and we've talked about this a little today already. And this is just a double white dwarf merger, which is even more relevant than I thought it would be, because it seems like more massive white dwarfs have more white dwarf red dwarf mergers. But the sort of violent evolution of merger remnants makes the survival of planetary bodies potentially unlikely. So we can easily wonder if merger byproduct contamination could be a sort of form of explanation of this lack of metal pollution at higher mass. So thanks to Gaia, we were able to get velocity distributions of white dwarfs in the solar neighborhood. And we know that massive white dwarfs are expected to have slow kinematics because they're young, and older stars get more stirred up around the galaxy. So we can actually even predict velocity distributions based on the age, the total ages of white dwarfs. But the merger sort of age reset makes things more complicated, and so that's a good way to flag merger remnants. This is some work by Sihao Chang, sort of looking at the velocity distributions of white dwarfs in DR2 over massive white dwarfs in DR2, and he was able to find that 20% of massive white dwarfs seem to be the products of mergers. If you're not used to galactic coordinates, I'm putting a little diagram here. This is VL and VB, so long VL and VB. The dashed line corresponds to sort of single star evolution, not assuming mergers, while the dotted line is assuming 100% merger remnants, and that's how he was able to find about 20%. So we thought it would be relevant to look at the snap sample and try to find the merger fraction and see that if we were to find a lot of mergers and a lot of high kinematics, that could explain the lack of metal pollution. So finally, this is what I get. These are the distributions of the velocities of the snap sample at masses above 0.8 or 3.5 solar masses. And I've put the expected velocity distribution assuming single star evolution right here. And I've also highlighted where the metal polluted massive white dwarfs lay. And what you're seeing here is that we're not really struck with many kinematic outliers, actually. And based on this, outliers would have been representative of mergers in the sample, but we really can't draw this conclusion just from these. It seems actually pretty consistent with single star kinematics. So that might be a little underwhelming, but you might wonder what's next. And while we increase the sample by over 3, by a factor of over 3, this stays pretty small number statistics. These sample are only 60 stars for the more massive. And so while that's a lot better than 12, it's still not statistically representative. So the obvious answer is let's increase the sample. Let's get even more massive white dwarfs to further rule out this possibility of merger remnant contamination being the cause for metal pollution. But we also should look at connecting white dwarf to metal pollution around white dwarfs to planetary occurrence rates around those B stars on the main sequence. And some ideas, some sort of clues for that would be to look at planetary disk lifetimes, or planetary architecture, or even binary fraction. So there's a lot more to uncover. There's a lot more mysteries to try to figure out why there is this lack of metal pollution at more massive white dwarfs, but it's pretty exciting things. So I'll leave my summary up, and I'm happy to take any questions.
Questions? Corinne?
Thanks, really nice talk. Have you guys thought about how easy or hard it is to detect metals in more massive white dwarfs compared to lower mass ones, either for this sample, given like how bright and hot they are, or in general if they're, I don't know, if the length of time the metals stay in the atmosphere changes with log G?
Yeah, that's a really good point. So diffusion times change for different masses and different temperature, but the sample is pretty hot and pretty bright. And for the massive ones, I have this number that might be of help. That's about for 20,000 Kelvin white dwarfs of 0.8 solar masses, it take about a day for the silicon to diffuse. So if we're seeing silicon, it's most likely currently accreting.
Thanks.
Yeah.
Hi. Yeah, thanks for the talk. So I know these are, in general, not as massive as some of the stars that McCrummen and Ilaria have been talking about, but other indications of merger could be magnetic field or rotational variability. So have you looked in your sample for indications of those?
Yeah, that's a great point. I haven't yet, but I think it would be interesting to look at, especially magnetic rates among the sample. Yeah, I'm thinking about it.
I think it would be very interesting and important to have some star formation synthesis to have some prediction of like how many of these could actually be single star, come from single star evolution. Because if they're mergers, then it doesn't tell us much about planetary systems, because as you say, even if they had some planets in the first place, it's very unlikely to survive.
Yeah, that's a great point.
Which one? I couldn't see who was first, so you guys decide. Jacques and Paul or whatever.
Thanks, Baya. I was related to Boris's question. Some of these are expected potentially to be mergers at a time in evolution where it wouldn't necessarily slow down the process. So you wouldn't necessarily expect inflated kinematics if it's a white dwarf and red giant, or if it's a merger on the main sequence or something. So I also think looking at at least some population synthesis models to see how many of those you expect, and seeing if it would disrupt the planetary system at that point. So I don't know if that's something you've thought about.
Yeah, I think it's a great further step to sort of confirm this. Yeah.
Hi. One of the very nice things of this sample is that it's largely unbiased. It's not like they were being targeted because they were known to be metal polluted. So thinking along these lines, I mean, do any of these have disks visible in the infrared?
That's a really good question. I'm not sure, but that would be something interesting. Maybe Boris knows. I don't know. Yeah.
Boris doesn't know.
Should I check?
Would be good to look into it, though. Yeah.
More questions? See how?
Thanks for a very nice talk. I can wonder, is there any correlation between the age of the white dwarf and the occurrence of pollution? Because the massive white dwarfs usually are much younger than the normal mass white dwarfs. Is that a factor relevant?
I think that as soon as the planets and planetesimals are disrupted, metal pollution could happen. So I could be wrong on this, but I don't think it should be that much of a factor. I think you should be able to see metal pollution as soon as the white dwarf is like disrupted in some way. Yeah.
Thank you.
Yeah.
Other questions? Yeah.
This is kind of related to his question, but when I'm not an observer, so do you have a rough estimate of the temperature span that your sample covers?
Yeah. Let me put it back up. Yeah. So these are the temperature.
Oh, I didn't even see that. Okay.
No, you're so good. And then for the more massive ones, they're closer to like 20,000 on average. Something like that.
Okay, thank you.
Yeah, of course.
We still have a bit of time if there are more questions. Alejandra?
Okay. Can you come back to your 9th slide? Slide number 9. Yeah. There. Maybe I missed something, but you're expecting less pollution from massive white dwarfs. Less observed one, and I don't see why that is something that is expected actually, because of well, they have a larger log G, so diffusion parameters, diffusion velocities are faster, and maybe it can be also related with the amount of hydrogen that is left. Have you thought about that?
I haven't. I think that at the temperatures that we're looking at, we still think that we should be able to see the same sort of metal sinking that haven't sunken yet for all these white dwarfs, but I haven't looked into the hydrogen. Yeah.
Okay, thank you.
Yeah.
Any pressing comments or quick questions? If not, let's thank Baya again.
Thank you.